Good afternoon. This is our third video lesson on volcanoes. All right, so as we discussed in class, for those of you that were able to come to class, eruption style is dependent upon three things: magma type, viscosity, and volatiles. Of course, all of this information is also in the narrated PowerPoints. So viscosity is going to be very important. And remember that viscosity refers to resistance to flow. So viscosity itself is going to be dependent upon three things: silica content, which we briefly discussed in class last week. The higher the silica content, the higher the viscosity, the less that magma wants to move and the more dangerous your volcano. Okay, viscosity is also dependent upon temperature. So a hot magma is going to be more runny and it's going to flow easier and have a lower viscosity and lead to less dangerous eruptions. So your effusive eruptions tend to, and that's mafic magma with our effusive eruptions, you tend to have a higher temperature magma and a lower silica content as well. Now volatiles are the volcanic gases, things like water vapor, carbon dioxide, hydrogen sulfide, and sulfur dioxide gases. These are discussed in the narrated PowerPoint. And the volatiles do a couple of things. The presence, and all magma is going to have some amount of volatiles. Some will have more than others. Your felsic magma tends to have a lot of volatiles. So the volatiles will actually reduce the viscosity a little bit, and that might sound good, but the bad outweighs the good in this case, and the presence of volatiles, dissolved gases in the magma, can lead to a dangerous buildup of gas pressure in the magma chamber. And as we discuss in the narrated PowerPoint, and we will discuss in class next week, if you have, say, a felsic to intermediate magma in the magma chamber, and it's got a bunch of dissolved gases in it, gases are easily compressible, and they are dissolved in the magma when that magma chamber is under pressure, and there's always going to be some kind of blockage in the conduit or volcanic neck. So it's kind of like a bottle of soda after it has been produced at the bottling plant. They're going to produce that bottle of soda under pressure. And when you buy the bottle of soda, let's say it's something clear, glass or plastic, you can see through it. When you first buy it, you don't see the carbon dioxide in it, but you know it's there. If you take off the lid, then you release the pressure and then you have the bubbles. And of course, if you shake that soda first or drop it on the floor and then open it, then you're going to have basically you're going to model a pyroclastic eruption. Okay, so what happens in the case of our volcanoes is if something happens like an earthquake and or a landslide that releases the pressure in that magma chamber, then those dissolved gases that are compressed are going to pop up into a gas form, and the volume of the magma will increase. But that magma chamber's full. There's nowhere for that material to go but to leave the volcano in a very violent manner, and that's going to be our pyroclastic eruption. Okay, so moving on to the next topic. This is our last video lesson, by the way, for volcanoes. Mount St. Helens. So if you come to class, you watch the narrated PowerPoint, we will briefly discuss the background of Mount St. Helens. We will not do that here. This is what I'm going to want you to know about Mount St. Helens for your third exam. I want you, and this is a short answer question here, I want you to know the sequence of events that happened. This was May 18th, 1980, Sunday morning, 8:32 a.m. First, we had a 5.1 earthquake, a shallow earthquake, and this was due to shifting magma in the chamber. And again, this was a shallow earthquake, so this really rocked the mountain. So in class, we will briefly discuss the fact that there was a bulge growing on the north flank of the mountain, and that was very worrisome. And what we saw in this eruption sequence is that the rock there, of course, was already weakened, because how do you form a bulge in rock in the brittle realm? And the answer is you have to form fractures. So that earthquake caused the north flank of the mountain to slide away. This was the largest landslide in recorded history. Well, that was like shaking your bottle of soda and then opening the lid. Okay, so the gases came out of solution. They popped up into a gas form. you have, an increased volume of your magma, and it's coming out of that volcano, whether you like it or not. So the pyroclastic eruption began, and we had both a vertical component up out of the summit vent, but we also had a lateral blast out the north face of the mountain because we lost the north flank of the mountain. And then this was followed by a lahar, or scary volcanic mud flow, because the snow and ice on top of the mountain melted. We'll discuss the lahar a little more in class. It's very deadly, and it can travel tens of kilometers away from the volcano, and it can put people in danger that otherwise would have been far enough away from the volcano. All right, moving on. Next topic. Not a happy topic here, but we cannot ignore tragedy. If it's part of history, we have to learn from it to not repeat it. Lake Nyos, Cameroon, Africa, one of 5 mantle plume hotspots on the African continent. This is back in 1986. So, a local villager had left this area to travel somewhere else for whatever reason, and then they came back and they discovered that everybody was dead. 1,700 people had died. There were no obvious signs of trauma. All the animals were dead. So they alert a nearby village. Word gets out to authorities. Word gets out to scientists, volcanologists all over the planet, including some folks from, I think it was University of Rhode Island. Anyway, so the scientists discovered a landslide scarp. So here's what they figured out. There was a dangerous buildup of carbon dioxide gas in the lake bottom. Why? It's a volcanic lake, a caldera really filled in with water. And carbon dioxide is one of the gases in the magma, and it was seeping into the lake. And you had a buildup of this carbon dioxide gas in the lake bottom, the bottom waters in the sediment. So they figured, maybe there was a small earthquake. It triggered the landslide. The landslide disturbed the bottom of the lake, and it released this huge bubble of carbon dioxide gas. So humans cannot breathe carbon dioxide and live. We need air, which is nitrogen and oxygen. And unfortunately, carbon dioxide gas is more dense than air. So the CO2 flooded the landscape and pushed the air way up high where people couldn't get it. And these people, they probably had no idea what was even happening because, carbon dioxide doesn't have a smell. Anyway, so they were asphyxiated and died. And we have taken measures to hopefully prevent this from happening ever again. There are now wells installed in Lake Nyos that are safely releasing carbon dioxide gas over time, so that it hopefully won't ever happen again. Okay, moving on around the room. Our next topic, I'm not sure about this light glare, but not much we can do about it. Okay, volcanoes and climate. So ash from large eruptions. Normally this is from stratovolcanoes, but occasionally from shield volcanoes, like in Iceland. Ash from very large eruptions sometimes can make it into the stratosphere. Not always, but sometimes. What's important about that is that we live in the lower layer, the troposphere, and the weather occurs in the troposphere, and the stratosphere is above. So if the ash, and also sulfur dioxide gas, get up into the stratosphere, well, that ash is not going to just fall back to the earth in the next rain. So it only takes a couple of weeks for this ash to encircle the globe, and then it is everybody's volcano. And this ash will stay up there for several months to perhaps a few years if it was like a Yellowstone eruption. And it blocks some incoming ultraviolet radiation and will cause a temporary temperature drop. Am I going to want you to also know an example? And the answer is, of course. 1815, Tambora in Indonesia erupted. 1816 is known in Europe as the year without a summer. They actually had crop failure because it just wasn't warm enough to grow the food that they needed. And there was famine. Also, Mount Pinatubo in the Philippines, 1992, and even Mount St. Helens in 1980 caused a little bit of cooling. All right, moving around the room some more. Next topic, we're going to try to keep this video to under 30 minutes so that it will load quickly onto YouTube. Okay, so if you were a volcanologist, which is a geologist who specializes in volcanoes, and you say were stationed in the Pacific Northwest, and you were going out and keeping an eye on volcanoes. You want to try to predict when they're going to erupt. So what specific kind of thing do the volcanologists look for? Okay, that first bullet there is the most important. the magnitude and frequency of shallow focus earthquakes. That is your most reliable precursor to an eruption. Did we see that with Mount St. Helens? Yes, beginning in March of 1980. Shape changes, and this can be done with tilt meters or GPS, laser surveying equipment as well. There was a bulge growing on the north flank of the mountain. Now, we didn't know that the north flank was going to slide away. Okay, we learned something. We learned something that day at Mount St. Helens. Part of the reason that 57 people were killed is that some of the people were to the north and they thought they were in a safe enough area, but because the north flank blew out, that pyroclastic flow went much further to the north than anybody anticipated. Gases, and you have to know your background readings. So you can't just never visit a volcano and wait for your seismometers to show some activity. You need to go there from time to time and take background readings. You need to know what the normal amount of gases escaping is so that you can know if there's been an increase in the gases. We monitor the heat flow coming out of the rocks. If the heat flow increases, it means magma is getting closer to the surface. We also monitor the temperature of hot springs. If the temperature of hot springs is increasing, that's also a sign that magma is getting closer to the surface. Moving around the room some more. Maybe we'll have less light glare over here. Actually, we'll probably have more light glare over here. Oh well. Okay, so we cannot stop volcanic eruptions. What can we do? We can monitor the volcano, and that's one of the jobs of the United States Geologic Survey, the USGS. What else can we do? We can create hazard maps, danger maps, have them ready, kind of know, how far the lahars are going to travel, how far we think the pyroclastic flow will travel, and so forth. Mount Rainier has sensors on the mountain, coming down the mountain flanks, well, I should say on the rivers, sensors that warn people downstream if a lahar is on the way. What else can you do? You need to have evacuation plans in place before you need them. And when it's time to evacuate, when you think it's going to erupt, you should go ahead and evacuate. And that last one there is only going to happen or be possible with some volcanoes, divert lava flows. So in the narrated PowerPoint, we talk about Iceland back in 1973. Shield volcano, they were able to divert a lava flow and save the harbor. And then Mount Etna, very active and well-behaved volcano on the island of Sicily. Back in 1944, it had an eruption, and lava was moving towards the city, and they were able to use concrete barriers and divert the lava flow. Okay, next to last topic, and I'm going to move around and see. God, that light glare is terrible. I can't get any more shade in here. Well, we're just going to go with it. Maybe if I adjust the iris again. Adjust the iris a little more. Does that help? It helps, but no, we can't really see it. Okay. Well, we'll read through this. Maybe if I stand at a different angle. Yeah, okay, that's a little bit better. At an oblique angle. Okay, so volcanoes and plate boundaries. There's 2 or 3 slides in the PowerPoint regarding this. These are the basics I want you to know, just 3 things. So your ocean to continent and ocean to ocean subduction zones will always give us stratovolcanoes. Those are the dangerous ones with pyroclastic eruptions. Hotspots in oceanic settings, like Iceland and Hawaii, will always give us shield volcanoes that have the effusive eruptions and are relatively kind and gentle. And then at the mid-ocean ridges, we have mafic melt, and we know that it's gentle eruptions that are producing brand new oceanic crust. Okay, last topic. Let's see how the light glare is doing. Now let's back up. And maybe go at an oblique angle, something to try to get rid of the light glare. Okay, is this gonna work? I think this will work. All right, our last topic for our last video lesson for volcanoes. So we spent some time discussing how dangerous volcanic eruptions are, but believe it or not, there have been some benefits. Okay, so volcanic outgassing early in Earth's history created the atmosphere we breathe and the water on our planet. Volcanic eruptions and intrusions earlier in Earth's history created the continents that we live on. Volcanic soil is very fertile, which might explain why people ever would have settled near active volcanoes like Mount Vesuvius in the first place. Precious metals that are so useful in our electronics are concentrated by magma systems, concentrated enough to make them economically worthwhile to go and get. Diamonds are brought to the surface by volcanoes, and you might think, I just don't care about jewelry, I don't care about diamonds. Well, diamonds are very useful as cutting tools. So lots of things in modern society have benefited from diamonds. Geothermal energy like they have in Iceland. And then, last but not least, when I was a kid, growing up and learning about Earth history and dinosaurs, scientists believed at that time that that life probably began in shallow, warm ocean basins. Well, we have tweaked that idea, and we now believe that life began at black smokers, which are volcanic vents at the mid-ocean ridges. So it's not really smoke, it's volcanic gases and nutrients, really, that are being released there at the mid-ocean ridges. And that will do it for our volcano lesson. Pretty short.